So this is lecture 3, example 3. Let's see what happens when we tweak the previous example a little bit. So now we're going to consider a sequence defined by an is equal to 1 on 2n minus 1. So when n equals 1, we've got 1. When n equals 2, we've got a third. When n equals 3, we've got a fifth, a seventh, and so on. It's only a tiny bit different to this 1 on 2n that we just considered. And indeed, it looks like it's getting smaller and smaller and smaller and closer to 0. So our conjecture is that an tends to 0 as n tends to infinity, just like before, which we could write also as the limit as n tends to infinity if an is equal to 0. This notation on the left here is implying that that limit exists. So if we want to prove that, we've got to prove that the definition of convergence to L equals 0 holds, i.e. that for all epsilon greater than 0, there exists some capital N, element of the natural numbers, maybe that capital N depends on epsilon, such that if little n is bigger than capital N, then the difference between the nth term of the sequence and that limit L, which actually, I'll write in the actual value of 0, is less than epsilon. So we're thinking, in particular, for all tiny values of epsilon, whenever you're big enough, the difference between your sequence and 0 is tiny. So let's just try the same capital N that we had before, because remember, we're trying to prove there exists. A good way to prove there exists is actually construct a possibility. So let's try capital N of epsilon is equal to 1 on 2 epsilon, just like we did previously. And again, there's this little detail of rounding down to make it an integer and adding 1 to make it convenient. That means that little n greater than capital N is always going to be greater than 1 on 2 epsilon. So what does that imply for n minus 0? Well, that says that is 1 on 2n minus 1 minus 0, and the absolute value just gives me 1 on 2n minus 1. Now, this denominator here is a bit of a nuisance, this 2n minus 1. We would really like something that was just something times n. We want 1 on 2n minus 1 to be less than 1 on something times n, because it's going to be a lot easier to manipulate. Well, that's going to be the same, equivalent to 2n minus 1 being greater than something times n. Can you think of a something that will make this true? And yes, the students in the actual lecture said we can think of a something. That something would be a half. So I'm going to replace that star with a half. Yep, that looks good. N equals 1, we've got 1 is greater than a half. N equals 2, we've got 3 is greater than 1. N equals 3, we've got 5 is greater than 1.5, and so on. It just, this side kills this side. And if I multiply top and bottom by 2 here, I get 2 on n. So I can conclude that 1 on 2n minus 1 is always less than 2 on n. And I know that n is greater than 1 on 2 epsilon. So what do I know? So this is a little aside here. I've got a second aside. If n is greater than 1 on 2 epsilon, what do I know about 2 on n? Well, let's see. It tells me 2n is greater than 1 on epsilon. This tells me 1 on 2n is less than epsilon. That tells me 2 on n is less than 4 epsilon. Oh, okay. So what I've got here is a less than 4 epsilon, and I want a less than epsilon. So that's telling me that this guess wasn't quite good enough. Not quite good enough, because I'm out by a factor of 4 from what I want. But it's close. It's really close. So let's continue, but make a slightly different guess for capital N. So again, just to recall, we've got an equals 1 on 2n minus 1. We want to show that for all epsilon greater than 0, there's this exists a capital N in the natural numbers such that n greater than capital N implies that the difference between the function and that limit of 0 that we've guessed is tiny. Let's now choose n equals 2 on epsilon. That's 4 times bigger than what we had before, pretty much, roughly. And then round down to make an integer and add 1 to make it convenient. That implies that little n is greater than capital N is greater than, beg your pardon, that implies that whenever little n is greater than capital N, that little n will also be greater than 2 on epsilon. So let's ask what's the effect on an minus 0 in absolute value. This is the same calculation as before. And then 2n minus 1. And as before, we note 2n minus 1 greater than a half n implies that 1 on 2n minus 1 is less than 2 on n. So this is less than 2 on n. And now let's see what, that's one aside. I have another aside over here. N greater than 2 on epsilon implies that 1 on n is less than epsilon on 2 multiplied by 2. 2 on n is less than epsilon. Yes, that's exactly what we want. And we're done. We've shown that this choice of n means that whenever little n is bigger than capital N, this consequence holds, that is, absolute value of an minus 0 is less than epsilon. Done.